Welcome to another Mathologer video. Today's video should be of interest to everybody who loves twisty puzzles, as well as all hardcore Mathologer fans. In 2010, 30 years after the Rubik's Cube rocked the puzzle world, it was finally proven that God's number for the Rubik's Cube is 20. What this means is that every single one of the 43 quintillion possible configurations of the Rubik's Cube can be solved with 20 or less turns. Now that's great, but what other fun and challenging Rubik's Cube maths problems are there? Well, there are a couple of closely related, more or less open problems that I really like and that are not that well known. To motivate these problems, let me ask you to picture yourself scrambling a Rubik's Cube. What are you doing there? Basically, you're trying to turn yourself into a monkey. Performing random twists on the cube until it looks suitably scrambled. This mental picture of a monkey messing around with a cube then raises a couple of very natural questions. First question: how many twists should the monkey execute to ensure that the cube is in a sufficiently random position? So random enough, for example, to create a fair starting position in a speed cubing competition. Second question: suppose, just for fun, you enter a monkey in a speed cubing competition. Happens all the time, right? On average, how many twists would it take for the monkey to solve the cube? Now, Mathologer is a very low budget operation and we can only afford one monkey. So this same monkey is both scrambling the cube and then unscrambling it. This means our monkey begins and ends with a solved cube, which motivates our third question. If a monkey begins scrambling a solved cube, on average, how many twists will it take for the cube to be solved again? On and off, over the past couple of weeks, I've been pondering these problems for the Rubik's Cube and its baby brother, the 2x2x2 pocket cube. I've been assisted by my new best friend, computer whiz Erich Tomanek from Switzerland. Let me tell you about some of the beautiful things we've discovered. Okay, the first thing to realize about pretty much all maths problems to do with twisty puzzles is that they are finite in nature. This means that it is usually pretty easy to come up with formulas or procedures that solve the problems. For example, to determine God's number for the Rubik's Cube, in theory, all you have to do is to figure out for every possible configuration what the least number of twists is to solve that configuration. Then God's number is simply the largest of all these numbers. It happens to be 20. But of course, even if such a calculation is fine in theory, in practice it would be truly horrendous. Even for a single configuration, it's not that easy to calculate the minimum number of twists. And of course, there are ridiculously many configurations to consider. So it's impossible to use this kind of straightforward brute force approach to calculate God's number. Unless, of course, you've got God's computer. Same thing with our three monkey problems. These sorts of problems are dealt with in general in the theories of stochastic processes, Markov chains and random walks. And there are theoretical solutions that deal with all three of them. The associated buzzwords are mixing time for problem 1, mean time from equilibrium for problem 2, and mean recurrence time for problem 3. However, again, because the complexity of the configuration space of the Rubik's Cube, using these formulas to find exact solutions to our problems appears impossible, or at least very, 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 very hard. Except there is a real surprise. The third problem, mean recurrence time, has a very simple solution. It turns out that the average number of twists a monkey needs to go from solved to solved is exactly equal to the number of configurations of the Rubik's Cube. How cool and how surprising is that? Anyway, this solution to our third problem works for the 3x3x3, for the 2x2x2, and for many other twisty puzzles. So for example, in the case of the 2x2x2, there are 3,674,160 configurations, and so it will take our monkey on average 3,674,160 twists to stumble his way from solved to solved. And for the 3x3x3, it will take on average about 43 quintillion twists. For those of you interested, at the end of the video, I'll sketch a really simple proof of this fact, which applies to all sorts of other highly symmetric twisty puzzles and probabilistic experiments. Really a great thing to know. But let's just continue with our story of discovery, okay? Now, this is the point where my new best friend Erich enters the picture. Among other things, Erich maintains a really fun webpage on which he simulates the famous infinite monkey theorem. This theorem says that if you have an immortal monkey type random letters on a typewriter, then the monkey will almost certainly type out the complete works of Shakespeare and the Harry Potter books and any other book you care to choose. You just have to be very, 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 very patient. Erich has a couple of virtual monkeys typing away on his page and reports on anything reasonable the monkeys have produced. Anyway, back to the cubes. The first thing Erich and I tried was to test the theoretical result that I just mentioned. So for the 2x2x2, we had a virtual slave monkey stumble from solved to solved over and over again. Our theoretical result says that the average number of twists required should approach 3.6 million. And that was indeed the case for our virtual monkey. What was particularly interesting was that we didn't have to wait very long for the correct average to roughly materialize. Just a couple hundred solves and the average settled down to approximately 3.6 million twists. That gave us confidence in our computer implementation of the problem. The next step was to attack our second problem. So the monkey was to repeatedly start with a random configuration and to solve from there. So we began by having the monkey execute a couple hundred random twists to hopefully give the monkey a random starting configuration, and we then had the monkey begin solving. With about the same number of solving sessions as before, the average number of twists to solve the cube panned out to be around 4.5 million. Now, a potential problem with this approach is that a couple of hundred random scrambling twists may not actually be enough to properly randomize the cube, which brings us back to our problem 1. How many random twists are enough to randomize a Rubik's cube? Well, this is an extremely tricky question that is also of keen interest to real-life cubers. It has been solved with an ingenious Gordian knot approach. The World Cubing Association, which provides the scrambles for cubing competitions, actually doesn't use random twisting at all to create their 2x2 and 3x3x3 scrambles. They used to execute 25 so-called non-redundant random twists for both the 2x2x2 and the 3x3x3 to randomize, but they don't do this any longer. What they do these days is to use a computer program called T-Noodle, which essentially does the following. It takes a cube, explodes it, and reassembles the pieces back into the cube completely randomly, which is actually not a problem. Okay, so now we have a truly random configuration. Unfortunately, only 1/3 of the configurations that can be made this way can actually be solved by twisting the cube. Luckily, there's a very easy test to check whether or not this is the case, and I actually already described such a test in an early video. And so, to create a truly random solvable scramble, the program just keeps exploding and reassembling cubes until a solvable configuration results. Neat, isn't it? Actually, I had a great discussion with Jeremy Fleischmann and Lucas Garon, two of the speedcubers behind T-Noodle, and discovered that there's a whole video worth of material about how they make sure that the different kinds of twisty puzzle used in competitions are scrambled fairly. I put some more info in the description of this video. So, instead of just scrambling by twisting and hoping for the best, we also ran our second experiment again using this confirmed totally random way of scrambling. So we scrambled using exploding and resembling, and then had the monkey solve with random twists. The result, as far as we could tell, was exactly the same as before. So approximately 4.5 million twists on average. Great. Well, not if you're the monkey. Now, just for fun, let's really enter our monkey into a speed cubing competition. Obviously, computers are a lot faster than humans at solving twisty puzzles. So to give us humans a fighting chance, let's give the computer a bit of a handicap. Let it solve a la monkey. Okay, so the god of speed cubing is Felix Zemdex, who, just like me, happens to live in Melbourne in Australia. His best 2 times 2 times 2 time is 0.79, believe it or not, seconds, and his best 3 times 3 times 3 times is 4.22 seconds. I know, completely insane, right? So, how would Felix fare against one of Erich's monkeys on his best day? Okay, first, the 2 by 2 by 2. Well, Erich's monkey scrambles at around 78,000 twists per second, and so 4.5 million twists will take about 58 seconds. And so, unless the monkey gets very lucky, he won't even get close to beating Felix. So, owners of supercomputers, here is your chance to implement the first deep blue monkey who can beat Felix. Should be a piece of cake. And now the 3 by 3 by 3. Well, in this case, Felix should be very safe for centuries to come. Just like in the case of the 2 by 2 by 2, we'd expect the average number of twists for our monkey to be greater than the number of configurations. And 43 quintillion twists at 78,000 twists per second comes to about 17 million years of fun random cubing. Okay, so finally, to ensure that this video receives the official seal of mathematics video-ness, let me show you a proof sketch that the average number of twists from solved to solved for a cube is exactly the number of configurations. That's the really cute result in this video, right? So the main ingredient of this proof is that every configuration of the cube is substantially identical. That may seem crazy, since the whole point of cubing is to get the cube into the one and only solved configuration. Here's what I mean by substantially identical. If you take a solved cube and a scrambled cube, and you remove all the color stickers, the underlying blank cubes are indistinguishable. So structurally, there are absolutely no differences between the different configurations of the Rubik's Cube. Okay, for our proof, we hand our monkey a solved cube and then, evil people that we are, we make the poor monkey twist the cube for all eternity. We then record all the step counts at which the monkey holds a solved cube in his hands. So since we started solved, there is a mark at 0. Now the monkey makes one twist. Then the cube's definitely not at solved, and so there is no dot across from 1. At this point, there's a real chance that the second twist will just be the first twist in reverse, which would bring us back to solved after only 2 twists, making for one happy monkey. Let's say that this has happened in our particular experiment, and so we would put a dot next to 2. Anyway, let's use orange dots to make the instances where the cube has returned to solved. Now, to find an approximation of the average recurrence time, we just make n twists, where n is some super huge number, and then divide n by the number of dots up to this point. Now, pushing n to infinity, this approximation will converge to the true average. All right. Now, all this tells us what we mean by the average, but of course it doesn't indicate what the average actually is. To get an idea of that, let's extend our diagram to the right, like this. So at the bottom, we now list all possible configurations, and with all the dots in place, indicating when the monkey visits these configurations, this is a complete record of the monkeys stumbling through the different configurations. Also, notice that after n twists, the diagram will contain exactly n dots, 1 for each twist. There are now 3 easy steps to figure out our average. First, unless he's the unluckiest immortal monkey ever, our monkey will eventually visit every single configuration. It's like waiting for the 6 in Ludo to appear. It may take like a zillion years, and sometimes in Ludo it feels like that, but eventually it will happen. Second, since none of the configurations of the cube is structurally distinguished in any way, after a very large number n of twists, we can get a good approximation of the average we are interested in by using the dots in any of the columns, not just the first one. Third, since after n twists there are exactly n dots in the diagram, the number of dots in each column is approximately this total number n divided by the number of configurations. And of course this simplifies like this. Again, as you push the number n to infinity, this approximation will turn into the equality we're shooting for. And except for a few fiddly details we've left out, that's the proof. The average number of twists it takes for the monkey to go from solved to solved is exactly the number of different configurations. The same proof applies to many other random experiments, those whose different states are indistinguishable. As an easy example, rolling a standard 6-sided die, there are 6 indistinguishable states, and so our argument also implies that on average it takes 6 rolls of the die to get a 6. Similarly, if instead of twisting a Rubik's cube, we simply have the monkey jump randomly from scramble to scramble, sort of like rolling a 43 quintillion-sided die, then the average number of rolls between solved configurations showing up is again 43 quintillion, exactly the same number as when the monkey moves by normal twisting. Not so intuitive, isn't it? But not hard to understand if you puzzle through the proof. It's also worth mentioning that there are actually 2 different ways to count the twists when scrambling cubes. Most people would count 1 twist for either a rotation of 90 degrees, 180 degrees, or 270 degrees, which equals 90 degrees in reverse. This way of counting is called the half-turn metric, and all the numbers in this video so far relate to this way of counting. The second way of counting only allows quarter turns, which I personally and many other mathematicians prefer. Here clockwise and counterclockwise quarter turns still count as 1 twist as before, but half turns count as 2. The second way of counting is called the quarter turn metric. There, half turn metric and quarter turn metric. So when people say that God's number is 20, they actually mean that God is using the half-turn metric. On the other hand, for a rival god using the quarter-turn metric, her number will be 26. And this was only proved in 2014. Now just for completeness sake, God's numbers for the 2x2x2 are 11 for the half-turn metric and 14 for the quarter-turn metric. What about our average numbers? Do our average numbers also change when we change from half-turn to quarter-turn metric? Well, the average from scrambled to solved for the 2x2x2 does change from roughly 4.5 million in the half-turn metric to 4.6 million in the quarter-turn metric. However, and this is again really nice, the average number from solved to solved stays unchanged, which is also pretty clear from the proof. What about the 3 times 3 times 3 with respect to the quarter-turn metric? Well, again, solved to solve is our usual 43 quintillion. What about scrambled to solved? Well, as with beating Felix, brute force computer simulations are completely out of the question here. On the other hand, I'd expect the numbers for scrambled to solved to be larger than that for solved to solve, both in terms of the half-turn and the quarter-turn metric. But maybe again not that much larger, so maybe also somewhere in the quintillions. Okay, here then is my challenge to all the real experts. Find the exact average numbers of scrambled to solved. I certainly think that the one for the 2x2x2 should be doable. Wouldn't it be great if a YouTube video like this one here actually inspired someone to do some serious research in Rubik's Cube mathematics? For the non-experts, here's a more modest challenge. Figure out the average number scrambled to solve of the 1 times 1 times 1 cube. Here I consider the 1 times 1 times 1 cube solved if it is in this particular fixed position in space. And the monkey scrambles by giving it quarter turns around the 3-phase axis. Right? So, finally, I should mention that there is a lot more really beautiful mathematics to be discovered in terms of mean recurrence time, even in situations that are not as symmetric as our twisty puzzles. The excellent PBS Maths channel Infinite Series did a very nice video on the classic problem in this respect, the problem of finding the expected number of random jumps it will take a knight to stumble from some corner of a chessboard back to the same corner. Definitely also check out this video and afterwards join me and a lot of other people and write to PBS asking them to reverse their terrible decision to cancel the wonderful Infinite Series channel. And that's it for today. Happy cubing!